Following this one, we'll be studying probability. And in the study of probability, counting possibilities in certain situations is very important. So in this section, we're going to talk about counting principles. Consider this problem. Suppose we flip a coin and then following that we roll a six-sided die, and we'd like to know all of the possible outcomes in performing these two tasks back to back. Well, the safest thing to do in counting the possible outcomes in a situation like this is to list them all and simply count them. So now when we flip a coin, we know that there are two possibilities. We can either get a head or a tail. And when we roll this six-sided die, we can get either a 1, or 2, or 3, or 4, or 5, or a 6. So one outcome is flipping a head and then rolling a 1. Another outcome is a head with a 2, head with a 3, head with a 4, head with a 5, head with a 6. And then we have to go through all of those possibilities if we flipped a tail on the flip of the coin. So the tail could be associated with 1, T2, T3, T4, T5, T6. And then, after listing all of the possibilities, we just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 possible outcomes. But a technique that can be utilized in this problem and in other problems where the counting is extremely inconvenient, if not impossible, if the number of outcomes is extremely large, is to do this. Just decide how many possibilities there are for the first situation, for the first event here of flipping the coin. Well, there are two possibilities, a head or a tail. And for rolling the die, it's 6 possibilities. And you simply multiply the possibilities. That is, we have 2 possible outcomes for the flip of the coin. We multiply times the 6 possible outcomes for rolling the die. 2 times 6 gives us the 12 total possible outcomes. Here's another situation. Suppose we want to determine the number of 2-letter words that are possible. Now we're using letters of the alphabet, and we'll just say that any 2-letter combination forms a word. All right? Even if it's AB, that's a word. Okay. Now how many are possible? Well, in a situation like this, the question will come up. Well, let's see, if we're multiplying our possibilities here, then we know that there are 26 letters in the alphabet. So when we choose the first letter for our first word, or when we determine the number of choices for the first letter, we're saying it's 26. Now the question becomes, do we include in the list of choices for the second letter the letter that we chose first? That is, if it's kind of like this. We can set it up almost like an experiment where we have the letters of the alphabet written on little slips of paper, and we throw those little slips of paper into a hat, and we shuffle them around, and someone draws a letter. Okay, so the letter is drawn, and there were 26 possibilities before the letter was drawn. Now, once that letter is read and recorded, what do? Do we take that letter that we had drawn out to begin with and put it back into the hat for the second drawing, or do we leave it out? Now that's called with or without replacement, and it makes a big difference in the outcome of the situation. That is, how many possibilities there are. Without replacement, that is, without including the first letter in our choices for the second one, it would look like this. Now remember, we're just multiplying the choices here. The number of choices for the first letter would be 26. The number of choices for the second letter, if we're talking about without replacement, without replacing that first letter back into the mix, is 25. So 26 times 25 would be 650. Now, with replacement, it's a somewhat different problem, but very similar. We have 26 choices for the first item, and then since we're replacing that first letter, we have 26 choices for the second letter as well. So 26 times 26, or 676. Consider this problem. Now, all of these are very similar to one another, but they all illustrate a certain kind of nuance in this whole idea. And by the way, the idea of multiplying choices along the way is called the fundamental counting principle. And it is our basis for counting the possible outcomes in situations like this. Okay, here we're going to use the fundamental counting principle again. But in this situation, let's say we have 8 books. And we have a small bookshelf, and the bookshelf can only accommodate 3 books. And we'd like to know how many arrangements of 3 books are possible, choosing those 3 books from a group of 8 books. Now let's understand this, that if I chose book 4 and then book 6 and then book 8, let's say, and that's one arrangement. Another arrangement, though, could include this same group of 3 books. You see, I could have the arrangement of 6, 8, 4. You see, a different arrangement even though it included the same 3 books. That's kind of an important idea. The order notion then changes the arrangement here and therefore changes the number in the count of possibilities. All right, that's just a very important idea in this kind of problem. Okay, so once again, we're just multiplying the possibilities. And let's see, if we're choosing for the first book to put it onto the shelf, we're choosing from a group of 8, so we have 8 possibilities. Once we have chosen the first book, see, I'm just multiplying my choices here for the 3 books on the shelf. Once I've chosen the first book and put it onto the shelf, it's no longer available to be chosen. So for the second book, there are only 7 possibilities, and for the third book, there would be 6. And multiplying these, we would find that there are 336 possible arrangements of the 3 books on the shelf, taking them from 8 books. Now, this situation has a name. This notion about order being important and so forth, this is called a permutation. And in the notion of permutations, order is an important aspect in the calculation of a permutation. Now, the word arrange or arrangement is often used in this kind of problem. And there's even a formula that's associated with permutation. Now, I'm going to show you the formula here. It's written down here. But really, I kind of shy away from using it because the fundamental counting principle, that is multiplying the choices, works really well in situations involving permutation. But I want to show it to you just to contrast it with another problem that is similar to this. And you might notice that this looks a little bit familiar to a formula that we used in a previous section. Well, let's see. Now notice that the notation here, the permutation of 8 things taken 3 at a time, is 8 factorial over 8 minus 3 factorial, you see. And so we have, simplifying, let's see, 8 factorial is 8 times 7 times 6 times 5 factorial. I'm going to stop right there because I know that 8 minus 3 is 5 down here. So this is 5 factorial. So in the denominator I have 5 factorial, and all of those factors cancel with all of these. We have the 8 times 7 times 6 that we talked about earlier using the fundamental counting principle. Consider this problem. It says, in how many ways can the letters A, B, C, D be arranged? And this is a very typical permutation type of problem. We're just multiplying the choices for each of the letters. So we have 4 letters, and we multiply our choices. So we have 4 choices for the first letter, 3 for the second, 2 for the third, and only 1 choice for the fourth. Now this is the same as 4 factorial, but it turns out to be 24. Here's a variation on the same theme. How many 3-digit area codes are possible if the first digit cannot be 0? Now, you see, although on this problem we could have used the permutation formula, on this problem it really doesn't work very well. And the fundamental counting principle needs to apply here. Because although we have 3 digits for our area code, we have a restriction on the first digit. And when restrictions come in, a lot of times the formula just doesn't work. So let's see, how many 3-digit area codes are possible if the first digit cannot be 0? Now there are 10 digits, and if this digit can't be 0, then we only have 9 to choose from. So we have 9 choices here. Then for this next digit, we have all 10 digits to choose from, so we have 10 choices, and we're talking about the possibility of replacement here. So we have 10 choices for the third digit. 10 times 10, 100 times 9, we have 900 then possible area codes under this restriction. Let's return to the book problem for a moment. Let's suppose that we have these 8 books that we talked about earlier, and let's suppose that we have a bookshelf that can accommodate all of them. We can put all 8 books on the shelf. So it's no surprise then that if we're choosing from this group of 8 and we're listing our choices for each book on the shelf, we have 8 choices for the first book, 7 for the second, 6 for the third, and so on all the way down to 1. That's just 8 factorial, which is 40,320. Another way to calculate it is to use our permutation formula. Now, it's a kind of an unusual situation when we have 8 things taken 8 at a time. Let me just show you how the formula works here. It's the permutations of 8 things taken 8 at a time. So in the numerator, it's 8 factorial. In the denominator, it's 8 minus 8, or 0 factorial, which we know to be 1. So 8 factorial over 1 is 8 factorial, and we get the same result, of course, as we did before. 8 books on the shelf, but it turns out that some of them are the same. That is, suppose I label this one A, and this one A, and this one A, and this one A. All 4 of these are labeled A, which implies that they are the same title. And then I'll label these 2 B, and then I'll label this one C, and this one D. Now, to accommodate this situation and to try to write the number of arrangements of these books, we might think about what we're talking about in terms of distinguishability. Now, for example, if I have book A, and then I have another book A, and then B, and then C, let's say. All right, that's a distinguishable arrangement of the 4 books. All right, now, what if I just take a couple of these and switch them around? Obviously, if I took A and B right here and switched them around, that would be a different arrangement, and we could see the difference. But what if I take the 2 A's and just swap them around? It would look exactly the same. That is, that second arrangement would be indistinguishable from the first arrangement. And a lot of times in situations like this, we want the distinguishable arrangements involved in a problem. So to calculate the distinguishable arrangements, we do this. We take the notion that if we're just putting all the books on the shelf without regard to the idea that we have duplications, then we know that we can do that in this many ways. Now, what we do is we take that and we divide out the duplications by realizing that this book is duplicated 4 times. We have 4 of this kind of book, and we have 2 of this kind. Now, just for completeness, we only have 1 of these 2 kinds. But it's the idea that we just take the 8 factorial and we divide by 4 factorial and then times 2 factorial. You see, and that divides out all these duplications, and away we go. Well, let's see, 8 factorial is 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times 2 factorial is simply 2. The 4 factorials go out, the 2 cancels with the 6, leaving 3. We multiply upstairs and we get 840. So 840 ways. All right, let's stay with this distinguishable permutation idea one more time. Suppose we have these letters. We have BBB, and then we have 5 of the letters T. And we'd like to know the distinguishable permutations for these 8 letters. Now we're talking about all 8 letters, you see. How many different ways can we arrange them that are distinguishable from one another? And it's the same idea as before. We just take, okay, we're going to arrange 8 things. So in the numerator, it's 8 factorial. And in the denominator, it is, well, we're dividing out duplications. We have 3 of that rascal, so we're dividing by 3 factorial. We have 5 of the T's, so we're dividing by 5 factorial. And then we perform the necessary operations here. We find this to be 56. Let's move away from the notion of permutation just for a moment. We're going to study another kind of problem now. And to introduce it, we're going to go back to the bookshelf problem, the one where we have a little bookshelf with, that can accommodate only 3 books. So we have 8 books to choose from. They're different from one another now. And I'd like to know how many groups of 3 books are possible to put onto the bookshelf containing 3 books. How many groups are possible? Now, a group of 3 books, if I have books A, B, and C, that is a group of 3. It's the same group of 3 even if I say this is C, A, B. See, same group of 3. So I don't want to count this twice. Now, if I was talking about arrangements, this would be 2 different items. But now I'm talking about groups. And that's what makes this a combination problem. All right, it falls into a different category when we talk about groups. And in combination problems, these are the characteristics. Order is not important. Now, order was important for permutation problems. Order is not important in combination problems. And that is a key factor to identify early on in our study of counting principles. All right, the word group, or sometimes committee, is often used in this kind of problem. All right, let's come back over here and make the calculation. As a combination, we use the combination formula to make the calculation. It is the combination of 8 things, because we're choosing from 8 books, and we're placing 3 of them on the bookshelf. So it's the combination of 8 things taken 3 at a time, which is 8 factorial over 8 minus 3 factorial times 3 factorial. Now, let's contrast this with the permutation formula. I just want to illustrate something to you here about the difference between these two. For the permutation formula, it would be 8 factorial over 8 minus 3 factorial. You see, they're the same in this part. The 3 factorial here in the combination formula is simply designed to take out or divide out those duplications that I talked about involving the same group being arranged, or I shouldn't use the word group and arrangement at the same time, but it's the idea that ABC and CBA are the same group. Different arrangement, same group. We want to divide those out. All right, and this accommodates that with that 3 factorial. Okay, so this is what happens, and our little trick for calculation is that we have 3 factors in the numerator starting with 8, so it's 8 times 7 times 6. And in the denominator, we have 3 factorial, so that's 3 times 2. And now the 6 cancels with these. We have 8 times 7, or 56, as the result. Here's another combination problem. It says, how many different 5-person committees can be formed from a class of 20 students? The tip-off here that it's a combination problem is the idea of a committee. A committee is just a group, and it doesn't make any difference whether you're the first person chosen for the committee or the last one. You see, order is not important here. It's the idea of a group. And so we know it's a combination problem. Now, it's the combination of 20 items, because there are 20 students in the class, taken 5 at a time. How many groups of 5 are there in 20? That's the idea. So to use the formula, and often the formula has to be used in combination type problems. So it's the combination of 20 things taken 5 at a time. We know in the numerator we're going to have 5 factors starting with 20, so we have this group of factors. In the denominator we have 5 factorial, which gives us this group of factors. And now it's a matter of canceling and multiplying and so forth. Now we can gain some efficiency by using the calculator, and in the calculator we find the combination formula like this. To make this calculation, you would press 20 and then press the math button, and that gives you a menu with several items at the top, and you need to scroll over all the way to the right. So you press the right arrow button 3 times and you get to a menu that is labeled, I think, PRB, for probability. And then you go down to item number 3, which is the combination formula. Now, we've already entered the n value. You see, you enter the n part of the formula first, and then you arrive here, press enter, and then now it's a request for the second part, the r part of our combination formula. So we enter a 5 and then enter again, and it makes the calculation for us as 15,504. This next problem involves aspects of both permutations and combinations. It's an interesting situation, and it doesn't occur very often, but occasionally it will come up. And here's how we want to think about it. It says a class consists of 8 males and 12 females. How many committees of 5 are possible if the committee must consist of 2 males and 3 females? You see, now in the previous problem we had a class of 20, we have a class of 20 here. In the previous problem we had a committee of 5, we have a committee of 5 here. Except we're designating the committee in a particular way in this problem. Now the idea that we have a combination, the combination idea is that we have 8 males, and from the 8 males, we're choosing only 2 to be on this committee. And the notion that we have 12 females and 3 of them can be on the committee. So that's the notion of the concept of combination. Now the permutation idea comes into play where we're thinking, well, all of these possible groups of males can be associated with all of these possible groups of females, you see. And so that's the multiplication idea, the fundamental counting principle notion, the permutation notion involved in the problem. All right, we would begin the analysis of the problem like this. We would think, well, let's see. Let's think about the number of ways that 2 males can be selected from this group of 8 males. So it's the combination of 8 things taken 2 at a time. All right, we'll make the calculation in a minute. And for the groups of females, we have 12 in the class. We can choose 3 for the committee. So it's the combination of 12 things taken 3 at a time. So the number of possible groups of 3 females is given by this formula. That's the idea. All right, let's come up here and put the idea of combination and permutation together. You see, if we take the number of male groups, each one of these male groups can be associated with each one of the female groups. So we have to take the number of male groups and multiply times the number of female groups. Now the number of male groups, we said, is the combination of 8 things taken 2 at a time. The number of female groups is the combination of 12 things taken 3 at a time. And now it's just a calculator punch. But here we have, if we're doing it by hand, for this, it's 2 factors in the numerator starting with 8, so it's 8 times 7. In the denominator, it's 2 factorial, which is 2. For this one, it's in the numerator, it's 3 factors starting with 12. 12 times 11 times 10. In the denominator, it's 3 factorial, which is 3 times 2. This turns out to be 28. This turns out to be 220. Multiplying, we find that the number of committees that are arranged in this very particular way is 6,160. Now we're going to look at an animation involving a combination or permutation problem. I'd like for you to try to decide which kind of problem this is as the problem is being read. Take a look. A combination lock will open when the right choice of 3 numbers from 1 to 40 inclusive is selected. How many different lock combinations are possible? Well, here's how we think about the problem. We notice that we have 3 numbers involved. We also notice that there are 40 choices for each number, and that order is important. You see, if we change the order of 2 of the numbers, then the lock won't open. So order is certainly important to us. That means then that what we have here is a permutation. So even though this is called a combination lock, in order to figure the number of sequences that are possible in opening the lock, it's really a permutation problem. And we use the fundamental counting principle. We simply write down the choices for each of the numbers involved. Now, since we can repeat the numbers, we have 40 choices in each position. All right, so 40 times 40 times 40 will give us the number of lock sequences that are possible. So there are 64,000 different lock sequences or combinations that are possible for this particular lock. Perhaps they should be called permutation locks instead of combination locks.